December 1941. The United States enters World War II following the attack on Pearl Harbor. Military planners in Washington confront an immediate crisis. The Army possesses inadequate armored forces for global warfare. Available tank production facilities operate at peacetime capacity, utterly insufficient for the conflict ahead. The M4 medium tank, later designated the Sherman, represents the Army's primary armored vehicle design. Initial production estimates reveal a sobering reality. Each unit requires approximately 300 labor hours from start to finish. Manufacturing records from early 1942 document this timeline. A tank beginning assembly on Monday morning reaches completion only after 2 full weeks of continuous work. Context matters here. Germany's armored forces already control most of continental Europe. Their factories produce Panzer III and Panzer IV tanks at established rates. Japan's military has occupied Manchuria, coastal China, and is advancing through Southeast Asia. American tank factories, meanwhile, complete perhaps 5 Sherman units weekly. Simple arithmetic reveals the problem. At this pace, the United States cannot field competitive armored forces before 1944. President Franklin Roosevelt, in early 1942, establishes production quotas that shock military and industrial leaders alike. He demands 45,000 tanks by December 1943. Army ordnance officers examine existing manufacturing capacity and recognize the mathematical impossibility. At 300 hours per tank, meeting this quota requires converting virtually every American factory into tank production facilities, an unrealistic proposition. The challenge extends beyond raw numbers. The United States, mere months earlier, maintained a peacetime economy. Factories produced consumer automobiles, household appliances, and commercial goods. The specialized equipment, trained welders, and industrial infrastructure for mass armored vehicle production simply does not exist. Military procurement officers can order tanks, but the nation lacks the physical means to build them at scale. If you appreciate detailed analysis of World War II industrial history, please like this video and subscribe to the channel. Leave a comment telling us where you're watching from. We read everyone. The solution emerges from an unexpected source: automotive executives. These industry leaders possess expertise in mass production systems, but no experience manufacturing military vehicles. The Roosevelt administration, however, recognizes their potential value. William Knudsen, a Danish immigrant who rose from factory floor positions to General Motors, President, receives appointment to head wartime production coordination. Knudsen brings fundamental insights from decades in automotive manufacturing. At GM, he supervised assembly lines producing vehicles at rates incomprehensible to military contractors. The Model T production system, perfected by Ford in the 1910s, achieved completion rates of 1 vehicle every 24 seconds during peak efficiency. Knudsen examines tank production procedures and identifies immediate parallels to problems the automotive industry solved 30 years earlier. Traditional tank manufacturing resembles craft production. Skilled workers hand-fit components, customize each vehicle, and treat every unit as a unique creation. This approach ensures quality but guarantees slow output. In February 1942, Knudsen convenes a working group including executives from Chrysler, Fisher Body, and Ford Motor Company. He pairs these automotive specialists with Army ordnance officers and poses a direct question: how would you manufacture 50,000 automobiles? This reframing proves crucial. The discussion shifts from building tanks the traditional way to applying proven mass production principles to armored vehicle manufacturing. The automotive executives identify immediate opportunities. Tank production in 1942 follows procedures largely unchanged since World War I. Individual craftsmen essentially hand-build each vehicle. Components require custom fitting. Workers drill mounting holes on site, adjust parts to achieve proper fit, and grind welds to specifications. Every Sherman emerges slightly different from the others, a romantic notion that creates catastrophic logistics problems. Consider the implications. If every tank is unique, spare parts must be custom fitted in field conditions. Battlefield repairs require specialized skills. Maintenance becomes exponentially more difficult. The British military experiences exactly these problems with their Matilda and Crusader tanks. Different manufacturers produce vehicles to the same basic specifications, but with enough variation that field mechanics require factory technical representatives present just to swap major components. American industrial planners determine this approach is unacceptable for the scale of warfare they anticipate. The solution requires fundamental reconceptualization of what tank manufacturing means. Fisher Body, a General Motors division specializing in automobile frames and body shells, received Sherman design specifications in January 1942. Their engineering team, led by Production Chief John Alder, immediately identifies the core problem. The tank is designed as one continuous welded structure. Manufacturing records detail the complexity. The hull alone requires over 5,000 individual welds. Most must be completed in strict sequence because certain joints cannot be reached until other sections are finished. Welders physically climb inside partially constructed hulls, working in cramped positions with cutting torches, spending hours joining armor plates at awkward angles. The process demands master craftsmen and creates severe bottlenecks. Fisher Body engineers propose a radical alternative. Divide the Sherman into 5 completely independent subassemblies that can be manufactured simultaneously in separate factory sections. The hull splits into distinct components: a floor section, 2 side assemblies, a front glacis plate unit, and a rear engine deck. Each subassembly would be built on dedicated production lines using specialized metal frameworks called jigs. These jigs represent the key innovation. Traditional tank building requires welders to measure, mark, and position components by hand. Precision depends entirely on individual skill. Jigs eliminate this variable. They hold armor plates in exact position, ensuring that every hull floor manufactured in Detroit is identical to every hull floor built in Chicago, with tolerances measured in fractions of millimeters. The modular approach dramatically reduces weld requirements. By designing subassemblies with flanges, time savings prove substantial. What previously required 3 master welders 2 full days can now be completed by 6 semi-skilled workers in 8 hours. The jigs perform the precision work. Operators simply follow procedures. Army ordnance officers initially resist this concept. They argue that bolted connections will prove weaker than continuous welds. They express concern that battlefield damage to one subassembly will require replacing entire sections. Fisher Body requests permission to conduct structural tests. Aberdeen Proving Ground in Maryland serves as the Army's primary weapons testing facility. In spring 1942, Fisher Body delivers several Sherman hulls constructed using their modular assembly method. Army engineers subject these vehicles to comprehensive stress testing. The test protocols are rigorous. Engineers fire 75mm armor-piercing rounds directly at joints between side panels and floor sections. They examine how bolted connections respond to combat-level impacts. The data proves decisive. Modular Shermans withstand identical punishment to traditionally built tanks. One test produces particularly compelling results. A 75mm round strikes the joint between a side panel and floor section, the exact connection Army officers worried about. The bolted connection holds. Moreover, the bolt pattern actually distributes impact stress more effectively than a single continuous weld line. The multiple connection points spread force across a wider area, preventing catastrophic failure. By June 1942, the Army adopts Fisher Body's modular method as the standard for all Sherman production. Fisher publishes a 400-page technical manual titled Simplified Tank Assembly Procedures and distributes copies to every contractor. Page 47 displays the subassembly breakdown with documented time savings. Hull floor assembly, reduced from 18 hours to 6 hours. Side panel assemblies, reduced from 24 hours to 8 hours. Turret basket assembly, reduced from 16 hours to 4 hours. Cumulative savings across all components. Approximately 120 hours eliminated from the production cycle before any additional process improvements are implemented. Fisher Body's innovation essentially invents flat-pack furniture concepts, 60 years before IKEA popularizes the approach for consumer goods. They demonstrate that a complex 30-ton armored vehicle can be treated as a collection of standardized parts that workers with minimal training can assemble by following numbered procedural steps. The Chrysler Tank Arsenal in Warren, Michigan represents purpose-built military manufacturing infrastructure. Construction begins in September 1940, a full 14 months before Pearl Harbor. Federal planners anticipate American involvement in the expanding global conflict and authorize construction of the most advanced armored vehicle production facility yet conceived. The main assembly hall, when doors open in April 1941, stretches 1,200 feet in length, equivalent to 4 American football fields placed end to end. Overhead crane systems capable of lifting entire Sherman hulls operate throughout the space. The facility's design borrows concepts from Ford's River Rouge plant, but scales them to tank dimensions. The conveyor system represents Chrysler's core innovation. A moving assembly line 40 feet wide advances at precisely 3.5 feet per minute. A bare hull frame begins at Station 1 on the north end. As it travels south through 113 designated workstations, teams add components in carefully choreographed sequence. Station assignments reflect detailed time-motion analysis. Station 12, suspension bogie installation. Station 28, transmission mounting. Station 45, engine installation, a 500 horsepower radial engine weighing approximately 1,200 pounds, lowered by crane in 4 minutes. Station 67, turret placement. Station 98, water pressure testing. Station 113, final inspection. By the time a hull reaches the south end, it is a complete, operational Sherman ready for test track evaluation. The facility's true genius lies in parallel subassembly lines feeding the main conveyor. While hulls move down the center, 26 separate side production lines build turrets, final drives, track assemblies, electrical harnesses, and gun mounts. Everything converges with split-second timing. A hull arriving at Station 67 pauses for exactly 18 minutes, while a completed turret built on line 7B starting 2 hours earlier is lifted by crane and set onto the turret ring. The coordination requires extraordinary precision. If line 7B falls 30 minutes behind schedule, the main assembly line experiences gaps. Gaps mean wasted capacity, thousands of workers standing idle while waiting for components. The facility employs 10,000 workers at peak production, organized into 3 8-hour shifts operating continuously. By mid-1942, Chrysler refines their process to complete 1 Sherman every 8 hours. Not starting 1 every 8 hours, finishing 1. That equals 3 tanks daily, 21 weekly, approximately 90 monthly from a single facility. Context: Germany's entire tank production across all factories in 1942 averages about 500 vehicles monthly. Chrysler alone produces nearly 20% of Germany's total output. Speed means nothing without reliability. Chrysler implements 47 inspection points along the main assembly line. Each Sherman undergoes systematic verification at every production stage. Station 98 houses water testing booths, where high-pressure hoses blast every hull seam checking for leaks. Turrets rotate through 50 complete revolutions, verifying bearing tolerances. Every gun breech receives 20 dry fire cycles. Vehicles failing any inspection are shunted to rework bays, but rejection rates by late 1943 drop below 2%, remarkable for a factory hiring thousands of workers with zero prior manufacturing experience. The low rejection rate reflects the effectiveness of jig-based production. When fixtures control positioning and alignment, human error is minimized. Workers cannot assemble components incorrectly because the jigs physically prevent improper assembly. While Chrysler perfects main assembly line operations, Ford Motor Company tackles a different challenge, producing complex turret components without skilled machinists. Ford's Highland Park plant in Detroit has built Model T automobiles since 1910. Turrets, however, present entirely different requirements. These are not simple stamped metal shells. Sherman turrets require precision gun mounts with recoil mechanisms, elevation gears cut to tolerances of 0.002 inches, and cast armor sections that must be machined to exact specifications so the turret ring rotates smoothly under combat stress. Traditional machining requires craftsmen who spent years learning their trade. You cannot hand an inexperienced worker a turret casting and expect acceptable results. Ford, however, has already solved this exact problem in a different context. The B-24 Liberator bomber program at Willow Run. The Willow Run facility, which opens in 1942, produces 4-engine heavy bombers using workers who have never seen an aircraft before. The secret: jigs and templates in such quantity that workers do not need to think. They simply follow color-coded instructions. Ford transfers this system to Sherman turret production with obsessive precision. Consider gun mount machining, originally an 18-hour job for a master machinist. Ford breaks it into 23 separate operations, each with dedicated machine tools and custom fixtures. Station A drills primary bearing holes using a template guaranteeing perfect alignment. The casting moves to Station B, where another fixture guides the cutting tool for the recoil cylinder seat. Station C handles elevation gear teeth. By Station W, that turret casting has been touched by 23 different workers, none of whom understand the complete assembly, but each of whom can perform their single task in under 15 minutes after 1 week of training. The time savings border on incredible. Complete turret machining from raw casting to ready for assembly component drops from 18 hours to 90 minutes. By August 1942, a 92% reduction. Ford publishes their methods in a technical report that October. Within 3 months, every Sherman contractor adopts similar jig systems. Fisher Tank Arsenal in Grand Blanc, Michigan, cuts turret time to 85 minutes. Pressed Steel Car Company in Pennsylvania achieves 95 minutes. Even smaller contractors like Pacific Car and Foundry in Seattle operate below 2 hours by early 1943. The jig system provides another massive advantage. It eliminates cumulative error. When a machinist hand measures and cuts, small inaccuracies compound. Maybe the first hole is 0.001 inches off. The second is 0.0015 inches off in a different direction. By completion, nothing quite fits. Jigs reset accuracy with every operation. Each fixture references original casting dimensions, so errors never compound. This means Ford can hire workers directly off the street literally. They run recruitment drives in downtown Detroit offering $1.25 per hour and have them producing combat-ready turret components within 9 days of training. Army testing at Aberdeen in October 1942 fires 500 rounds through each contractor's turrets, checking for mechanical failure. Pass rate, 99.4%. These are not inferior products made by unskilled labor. They are superior products made by superior systems. 7 different factories across America build Sherman components using different suppliers, different machine tools, and different raw materials. Without intervention, this produces 7 different versions of the same tank. A turret built in Michigan would not fit a hull from California. Tracks from one factory would not match drive sprockets from another. This exact problem plagued British tank production early in the war. Different manufacturers produced Matildas and Crusaders with such variation that field mechanics needed factory representatives present just to swap major components. American planners determined this is unacceptable. The solution: interchangeable parts at industrial scale. Eli Whitney invented interchangeable parts concepts in 1800 for musket manufacturing. But Whitney's muskets contain perhaps 40 components. A Sherman has over 8,000 distinct parts. Achieving true interchangeability across multiple factories built by different contractors requires standardization never before attempted. The War Production Board establishes the Tank Standardization Committee in February 1942. They create master gauges, not blueprints or technical drawings, but actual physical objects, precision ground metal templates defining exactly what a correct part looks like. Every contractor receives a set of 340 master gauges for critical Sherman components. The turret ring gauge, for example, is a machined steel circle ground to a tolerance of plus or minus 0.005 inches. If your turret ring matches that gauge, it will fit any Sherman hull in existence. If it does not match, you scrap it and restart. Factories implement go, no-go inspection systems at every stage. A go gauge slides into or over a correctly sized part. A no-go gauge, slightly larger or smaller, will not fit a correct part, but will fit an out-of-spec part. Workers do not need to read micrometers or understand tolerances. They simply verify that the go gauge works and the no-go gauge does not. This binary system is foolproof. Fisher body inspectors in Grand Blanc check 50 random transmission housings per shift using the same gauges as Chrysler inspectors in Warren. If both factories' parts pass their respective gauges, those parts are guaranteed compatible. The proof arrives in combat. November 1943, North Africa. A Sherman from Chrysler Tank Arsenal throws a track during operations. The replacement final drive comes from Fisher Body's Grand Blanc plant. Track sections come from Ford. Bogie wheels come from Federal Machine and Welder in Ohio. The repair crew bolts everything together in 40 minutes without modification. Not a single hole requires re-drilling. Not a single bracket needs bending. Everything fits on the first try, because 7 factories 2,000 miles apart all build to identical exacting standards. By mid-1943, interchangeability is so reliable that the Army stops tracking which factory built which Sherman. They simply order M4A1 medium tank and accept delivery from whoever has capacity. Ordnance depots in England stock spare parts from mixed sources, and mechanics never ask where a component originated. All the jigs and gauges accomplish nothing without people to use them. In 1940, America possesses perhaps 50,000 skilled welders, machinists, and metal fabricators craftsmen who spent years learning their trade. The Sherman program alone needs 200,000 workers. Add aircraft, ships, artillery, and every other weapon system, and the math becomes impossible. The traditional approach, apprenticeships, trade schools, years of training, would take until 1950 to build the workforce needed in 1942. Industry implements what sounds insane, breaking master craftsmanship into micro-tasks so simple that anyone can learn them in days. This concept, called labor dilution, becomes the secret weapon of American production. Consider hull welding, traditionally requiring 2 years training to master. A skilled welder needs to understand metallurgy, recognize different steel grades by spark pattern, adjust torch temperature dynamically, and execute dozens of different weld types depending on joint geometry and load requirements. Chrysler's training department, led by Charles Sorensen, who learned manufacturing under Henry Ford himself, analyzes hull welding and discovers it consists of exactly 47 distinct operations. Most are identical, running a bead along a straight vertical seam between 2 plates held in a jig. Only 7 operations require real complexity welding, curved sections, or overhead joints. Sorensen splits the job. 40 operations become Class B welder tasks requiring 9 days training. The 7 complex operations become Class A welder tasks, handled by experienced craftsmen, now freed to focus on genuinely difficult work. The training is incredibly specific. Class B welders at Chrysler do not learn welding. They learn vertical fillet weld, 3/8" mild steel plate, 90-degree joint, stationary position. That is the entire job. They practice that one weld type 8 hours daily for 9 days straight, running thousands of practice beads on scrap steel until muscle memory develops. On day 10, they proceed to the production floor and run that exact same weld on actual Sherman hulls. Nothing else. If a different weld type is needed, a different worker handles it. The system unlocks an entirely new labor pool. By late 1942, approximately 40% of Sherman production workers are women, many of them housewives with zero industrial experience. The Rosie the Riveter image is famous, but reality proves even more impressive. These are not propaganda figures. They are genuinely skilled operators performing complex manufacturing tasks. Rose Monroe works at Ford Willow, Run plant installing turret bearings, a job requiring precision measurement to 0.001 inches. She had been a waitress 6 months earlier. Ford's records show her rejection rate actually lower than male workers she replaced, because she follows checklist procedures exactly without improvising. The age range is equally notable. Chrysler hires 16-year-old boys straight from high school for track assembly work. United Motors hires men in their 60s and 70s for gauge inspection roles, requiring good eyesight but not physical strength. By 1943, the average Sherman worker has 11 months total manufacturing experience, and they produce vehicles that survive tank battles in the Ardennes forest. Building Shermans in 10 hours means nothing if raw materials do not arrive at factories at precisely the right moment. Too early, and you pay to store mountains of steel, copper, and rubber, tying up capital and warehouse space. Too late, and entire assembly lines stop while 10,000 workers stand idle waiting for parts. The War Production Board faces logistics challenges that make D-Day planning appear simple. Coordinating delivery of hundreds of different materials to 7 major tank factories without choking America's already overloaded railroad system. One Sherman consumes substantial raw material. The hull alone needs 15 tons of rolled armor plate in 4 different thicknesses, 2 inches for glacis, 1.5 inches for sides, 1 inch for rear, and 0.5 inches for floor. That armor comes from exactly 3 American steel mills capable of the specialized rolling process: Bethlehem Steel in Pennsylvania, Carnegie Steel in Ohio, and U.S. Steel in Indiana. Each mill also supplies battleship armor, destroyer hulls, and structural steel for Liberty ships. The WPB allocates their output by priority code. Sherman hulls are a A1, the highest rating, theoretically receiving first claim on production. But battleships are also a 1. You cannot tell the Navy their ships come second. Then there is the engine situation. Most Shermans use the Continental R975 radial aircraft engine, a 9-cylinder design originally for trainers and light bombers. Continental's main factory in Muskegon, Michigan, can produce 800 engines monthly by late 1942. But Sherman production hits 1,200 tanks monthly that same year. The shortfall is covered by licensing the design to 6 other manufacturers: Chrysler, Lycoming, Giberson, and others, who must be supplied with specialized aluminum alloys for cylinder heads. That aluminum comes from Alcoa plants in Tennessee and Washington, which also feed B-17 and B-29 bomber programs. The War Production Board solves this through synchronized scheduling. Every Monday morning, representatives from the 7 Sherman contractors, their major suppliers, and the Railroad Coordination Office meet in Washington, updating a massive wall chart showing material flows. If Chrysler needs 500 engines delivered to Warren by Thursday, the chart shows Continental shipping 200 from Muskegon on Tuesday, with remaining 300 coming from Lycoming in Pennsylvania on Wednesday. Railroads allocate exactly the right number of flat cars to those routes. pulling them from civilian freight if necessary. This system has zero error tolerance. March 1943, a rail bridge collapses in Ohio, cutting the primary route from Carnegie Steel to Fisher Tank Arsenal. Within 6 hours, the WPB reroutes 40 flat cars of armor plate through a southern route, adding 200 miles, but keeping delivery on schedule. The trains arrive at Grand Blanc 14 hours late, meaning Fisher's Tuesday morning shift starts with a 14-hour material shortage. But the WPB anticipated this and ordered Bethlehem Steel to ship an emergency consignment via express freight, arriving Tuesday afternoon. Fisher never stops production. By mid-1943, the 7 major Sherman factories collectively receive 22,000 tons of raw material weekly via 1,400 separate rail shipments. The WPB tracks every shipment in real time using telegraph updates from rail yards. What did all this accomplish? Between February 1942 and July 1945, American factories produced 49,234 Sherman tanks. That exceeds Germany's entire wartime production of all tank types combined. But raw numbers tell only part of the story. Timing matters. By June 6, 1944, D-Day, Allied forces have enough Sherman stockpiled in England to equip entire armored divisions with backup vehicles already in reserve. When 2nd Armored Division hits Omaha Beach, they land with 186 Shermans and another 40 in reserve ships offshore. When they lose 23 tanks the first week of fighting, replacements arrive from depot stocks within 72 hours. This creates completely different warfare than what Germans are fighting. A Panther or Tiger tank is arguably superior to a Sherman in one-on-one engagements. Better armor, better gun, better optics. But Germany produces roughly 6,000 Panthers and 1,300 Tigers during the entire war. When a Panther breaks down or gets knocked out, replacement parts take weeks to arrive, if they arrive at all. German tank crews in France cannibalize disabled vehicles just to keep remaining tanks operational. Meanwhile, American armored divisions can afford aggression because they know losses will be replaced. They can send 5 Shermans to flank a single Panther, because even if they lose 2 in the process, 3 more arrive next week. The 10-hour assembly time fundamentally changes military strategy. Generals plan offensives knowing their armored strength will actually increase during campaigns, not decrease. 3rd Army under Patton burns through Shermans at ferocious rates during the drive across France in summer 1944. Losing an average of 30 tanks weekly to combat and mechanical breakdown. But depots deliver 45 weekly. Patton's effective armored strength grows even while taking casualties. That is warfare Germany simply cannot match. The production methods live on long after the last Sherman rolls off assembly lines in 1945. Japanese industrial observers tour American tank factories in 1950 as part of post-war reconstruction planning. They are stunned by modular assembly systems. Toyota engineer Taiichi Ono specifically studies Chrysler tank Arsenal's synchronized supply chains when developing what becomes the Toyota production system and just-in-time manufacturing in the 1960s. The concept of breaking complex products into simple sub-assemblies, using jigs to eliminate skilled labor requirements, and coordinating supplier deliveries to eliminate inventory, that is standard practice now in every modern factory. But it was revolutionary in 1942. Ford's jig and fixture library from Sherman production becomes the foundation for their post-war manufacturing renaissance. The same templates and quality control systems producing turret components in 90 minutes are adapted for transmission housings, engine blocks, and chassis components in the 1949 Ford sedan. The modular design philosophy appears in civilian products throughout the 1950s. Appliances, electronics, furniture, all benefiting from wartime engineering breakthroughs. The Sherman itself gets criticized by historians who focus on armor and firepower deficiencies. But those critics miss the point entirely. The Sherman won because 49,234 of them showed up. The engineering triumph was not in the tank's design. It was in the system that could produce combat-ready armored vehicles faster than the enemy could destroy them. That is the real story of how engineers designed the Sherman to assemble in 10 hours instead of 300.